Welcome back to Control System Lectures. This video is a continuation of the series on how to sketch a Bode plot by hand. We'll build off the last lecture where the transfer function was a constant, and describe the Bode plot for a transfer function that has either a pole or a zero at the origin. If you missed the last lecture, you can click on the annotation in the lower corner, and it'll open in a new window. Before we get started, I want to just briefly explain what a pole and zero are in the context of a transfer function. If you replace the operator s in a transfer function with a value that causes the result to approach infinity, that value of s is called a pole. Similarly, if there's a value of s that causes the transfer function to equal 0, then not surprisingly that value is called a zero. A pole at the origin means that s equals 0 when the transfer function approaches infinity. A transfer function with a single pole at the origin can be written as 1 over s. And a transfer function with a single zero at the origin can be written as just s. When s equals 0, the result of the transfer function is also 0. So now let's talk about what the frequency response looks like for a transfer function with a single pole at the origin. As we just said, the transfer function is 1 over s. This transfer function is very important in control systems because it's the Laplace transform of an integrator, but we'll talk more about that later. For now, we can solve for the frequency response by setting s to j omega, which for our transfer function is negative 1 over omega times j. A real quick side note about j. J equals the square root of negative 1. Therefore, 1 divided by j is 1 over the square root of minus 1. If you multiply the top and bottom by the square root of minus 1, you can see why 1 over j is just equal to minus j. Okay, back to the problem at hand. We found that there is no real component of the result, and so we can write that as 0, and that the imaginary component is negative 1 over omega. Using this information, we can solve for the gain of the transfer function. This is the magnitude of h of j omega, which is positive 1 over omega. And the phase of the transfer function is the argument of h of j omega, and this equals minus 90 degrees. To see this graphically, you can plot the real and imaginary components on an axis. In our case, the real component is 0, and the imaginary component is minus 1 over omega. The length of the vector from the origin to that point is the magnitude, which you can see as 1 over omega, and the phase is the angle off the positive real axis, or minus 90 degrees, just like we calculated. Another way to look at this is to draw the block diagram and set the input to the transfer function equal to a pure sine wave of frequency omega. Remember that 1 over s is just an integrator, so the output is the integral of the sine wave, which can be solved easily to be minus 1 over omega times cosine omega t. You can see that the gain is 1 over omega, and both the negative sign and the cosine contribute to the phase. If we look at this in the time domain, the input is a pure sine wave, which is this blue line. And the output is a negative cosine wave, which I'll draw on the same plot so you can see the relationship between the two. And you can see that the output, which is the green line, is lagging behind the blue line by 90 degrees. Or we say that it has a negative 90 degrees phase shift. All three of these techniques produce the same gain and phase for this transfer function. But we don't have to do any of that math in the future if we can remember what the frequency response looks like for a transfer function of this class. So let's get to the Bode plot already and see what this looks like. We've just solved for everything we need to plot the gain and phase at all frequencies on a Bode plot. Remember, the vertical axis is in decibels, which is a log scale, and then we also plot the frequencies horizontally on a log scale. And we calculated before that gain is 1 over omega. So when omega is 1 radian per second, then the gain is also 1. And when we convert this to decibels, it becomes 0, and we can plot that point on the gain plot. When omega is 10 radians per second, then the gain is 1 over 10, or 0.1. And when we convert that to decibels, this just equals minus 20. And we can plot that point on the gain plot. And since 1 over omega is a linear equation, we can just draw a straight line between the 2 points. But can we extrapolate that to the next point by drawing another straight line? Let's find out. When omega is 100, then gain is 1 over 100, and when we convert that to decibels, it equals minus 40 dB. And so we can see that it is continuing this linear line. And we can draw this in either direction for all frequencies. The slope of this line is said to be negative 20 dB per decade. And what that means is for each multiple of 10, the gain drops by 20 dB. And on a log scale, each multiple of 10 is called a decade. Drawing the phase for this transfer function is simple, since it's just minus 90 degrees at all frequencies. So now when you come across the transfer function 1 over s, you don't have to do the math. You can just draw these gain and phase plots directly. But you might be asking right now, how often does the transfer function 1 over s arise all by itself? What if the function still has a pole at the origin but is slightly more complicated? For example, 5 divided by s, or 3 divided by s squared. Now how can you draw the Bode plot directly from this? Well, you can rewrite the first transfer function as a gain of 5 times 1 over s, and you can rewrite the second transfer function as a gain of 3 times 1 over s times 1 over s. And now because of the properties of logarithms, we can take the frequency response of each part individually and add them together on a Bode plot to get the frequency response of the entire transfer function. And that's one of the main reasons why we plot on a log-log scale, so that we can take advantage of adding these frequency responses together rather than having to multiply the responses, which would be much more difficult. So for this second transfer function, we can take the response of a gain of 3 and the response of 1 over s plus the response of 1 over s to get the response of 3 over s squared. Now from the last video, you'll probably remember that the transfer function for a constant of 3 is just 20 log 10 of 3, and that the phase for a positive constant is just 0 for all frequencies. And we just learned that 1 over s has a slope of minus 20 dB per decade on the gain plot and a phase of minus 90 degrees. And so since we have two of these 1 over s's, we can just duplicate those on the Bode plot. So now to get the full response of the system, we just add these three lines together. And when you do that, you'll get another linear line that has a negative slope of 40 dB per decade with a gain added to it of 20 times the log of 3. And the phase would just be 0 minus 90 degrees, which is minus 180 degrees for all omega. So I've spent this whole time talking about a pole, but what about a 0 at the origin? How can we solve for that? Well, luckily we don't have to go through all this math again. We can use the properties of logarithm again and say that s is just equal to 1 divided by 1 over s, and 1 over s is a pole. So now we can state that the frequency response for s is just the frequency response of gain 1 minus the frequency response of a pole. The gain of a transfer function of 1 is just 1, which is equivalent to 0 dB, and it also has a phase shift of 0. And when you take 0 and subtract something from it, you just get the negative of what that something is. So we can easily draw the gain of a 0 just by drawing the negative of a gain of a pole, which is just a reflection about the real axis. And we can do the same with phase. So phase becomes positive 90 degrees for a 0. And something else to think about, if you had a pole times a 0, which would just be s divided by s, you would expect the transfer function to go to 0. And if you sum the responses of both the red line and the green line, you'll see that the gain does go to 0 for all omega. And the same applies to frequency, so the math works out. In addition, now you can draw the frequency response for any combination of constants, poles, and zeros at the origin using this technique without ever having to do the math now. In the next lecture, I'll explain how to draw the frequency response of real poles and zeros